Alright, problems number 100 and 102 each deal with double replacement cations and anions that swap partners with each other. So for instance, if you had two chemical compounds, AB and CD, right, the cation A would swap places with the cation C, and you'd end up with AD and CB. So cations and anions switching places. Whenever you have one of these double replacement reactions, one of the products has to be one of three things. So it can either be a gas, it can be a precipitate, which is a solid, or it could be water. All right, in this first reaction, you're told that a reaction occurs when hydrosulfuric acid, which is H2S, is mixed with an aqueous solution of iron 3 bromide. So again, you're told iron 3, that Roman numeral 3 means that iron has a 3+ charge. So if iron has a 3+ charge, you need 3 bromines, which have a 1- charge to cancel it out. This is an ionic compound. Okay, so we've got our two reactants here. If a double replacement reaction were to occur, the cation in this H2S, which is H+, right, we get our H+ there, there's two of them, would end up meeting up with this bromine from the second compound. And our iron from the second compound would bind up with that sulfur from the first compound. Okay, so we can come up with the chemical formulas based on the knowledge that the cations and anions will swap partners. And again, this is a matter of balancing charges. The most likely charge for an H ion is +1. The most likely charge for a bromine ion is -1. So you need one of each to cancel each other out. We're told earlier that this is iron 3, so iron's got a 3+ charge. The most likely charge for sulfur is a 2-. So in this case, you need 2 irons to cancel out the charge of 3 sulfurs. From here, you can balance the equation, right? You do that using coefficients, so that's why we end up with a 3, the 2, the 6, and the 1 here. And you're told the states of the different things in the problem. So hydrosulfuric acid is aqueous. Iron bromide is aqueous. HBr, so they call it hydrogen bromide. You could also call it hydrobromic acid, is aqueous. And this last guy here, this iron 3 sulfide, is a solid. If we want to get the net ionic equation from this, first thing we need to do is get the complete ionic equation. When you want to get a complete ionic equation from a balanced chemical equation, basically what you do is you break up everything that is aqueous, so like H2S, FeBr3, and HBr, into its constituent ions. You leave the things that are solids alone. So in this instance, our 3 H2S's will break up into 6 H pluses and 3 S2 minuses. Our FeBr3 will break up into 2 Fe3 pluses and 6 Br minuses. Again, we use these coefficients and we carry them through here. So the 3 carries through to all these H's and S's, the 2 carries through to all the Fe's and the Brs. And on the right side of the equation, this HBr is going to break up into 6 H pluses and 6 Br minuses. The Fe2S3 stays on its own. In going from a complete ionic equation to a net ionic equation, what you need to do is eliminate things called spectator ions. So spectator ions are present on both sides of a complete ionic equation. And basically what spectator ions are they're things that are present in solution, but they're things that don't participate in an actual chemical reaction. In this case, we've got 6 H pluses on the left and 6 H pluses on the right. We also have 6 Br minuses on the left and 6 Br minuses on the right. Our hydrogens and our bromines are spectator ions, so we eliminate them to get our net ionic equation. So our final step is to take these things that were dissolved and not spectator ions and move them down, and take the solid and move it down to our net ionic equation, and you get the answer here. The 3s2 minus plus 2fe3 plus goes to fe2s3. Problem number 102 involves another double replacement reaction. And in this problem, you're told that a reaction occurs when sulfurous acid, which is H2SO3, is mixed with an aqueous solution of sodium hydroxide. Chemical formula for sodium hydroxide is NaOH. You get that again by balancing charges. Na is +1, and OH minus is -1. So you need 1A and you need 1 OH minus to balance this off. We're told that the reaction produces aqueous sodium sulfite. So there's your Na2SO3. Again, that's something you calculate by balancing charges. So Na has a plus charge, each charge. And you got to figure out what the other product is here. Well, if it's a double replacement reaction, what's going to happen is, again, the cations and anions are going to swap partners. So in our Na2SO3, what you have is a cation from sodium hydroxide and an anion from sulfurous acid. The other product is going to be the cation from sulfurous acid, hydrogen, bonded with the anion from sodium hydroxide, OH. When you put an H together with an OH, you get water. So water here is a liquid. You can assume that when you're talking about any acid, it's aqueous, unless people specify otherwise. And besides that, you're told the states of everything else. So sodium hydroxide is aqueous, and sodium sulfite is also aqueous. So this, in fact, is a special type of double replacement reaction. This is called a neutralization reaction. And a neutralization reaction occurs whenever you're mixing an acid and base together. In this case, H2SO3 is the acid, mainly because you're told it's called sulfurous acid, but acids usually start with an H. And NaOH, sodium hydroxide, is a base. A lot of bases end with OH. So whenever you mix an acid and a base together, you form two things. You form a salt. So a salt doesn't just have to be table salt. It's not just NaCl. Basically, it's anything that has a cation that comes from a base and an anion that comes from an acid. So you form that salt, and the other thing you form is water. In this case, H2O is our other product. From here, the strategy is similar to the one we employed in 100. You break up everything that's aqueous into its constituent ions. So that means also our sulfurous acid, our sodium hydroxide, and our sodium sulfite all get broken up into ions, and our water is left alone. So if you look at the complete ionic equation here, that's what it looks like. We have our 2H pluses, our SO3 2 minus, 2 Na pluses, 2 OH minus. Again, this 2 carries through to everything in it. We don't break up the SO3 into separate S's and O's because sulfite is an ion in its own. So when we're breaking up these compounds, we break them up into their constituent ions, not into every single element that's involved. So that's why SO3 2 minus stays together and OH minus stays together. On the right side, we break up our sodium and our sulfite, and we're left with this complete ionic equation. From here, we want to eliminate the spectator ions. So our spectator ions, again, are going to be the same on both. In this case, it's sodium. And we've got 2 sodiums on each side, and sulfite. We've got 1 sulfite on each side. You eliminate those, and you end up with your final net ionic equation. Because everything here has 2's, you got 2 H's and 2 OH's and 2 H2O's, you can cancel out those 2's as well. And so you'll just end up with H plus aqueous plus OH minus aqueous goes to H2O liquid. So that's problem number 102.